Good afternoon, everyone. We're here today with Tom Campbell, Farbod Khashnud, and David Chartrand. Farbod is the team leader conducting Tom's physics experiments, which are variations of the double slit experiment, with David Chartrand as research assistant. Farbod, thanks for being here, and please tell us what the current status of the experiments are.
Thank you very much, Donna, for the introduction. I would like to share with you some of the work that we have been trying to do. We have started to do the double slit experiment in combination with the quantum entanglement. We have some initial results for our interference data. This is some sort of interference, but we think that we have to improve it. We have to improve it so we get a better clear interference pattern. And one thing we have noticed that we have to do is, if I share with you another screen, is if you look at our experiment, this is our experimental setup that we have some collimators, some filters, and the beams of the photons are coming from the bottom and reaching to the polarizing beam splitters, these two polarizing beam splitters, and then it can go to A prime, and B prime, depending on the polarization of the photons. If they are horizontal, they transmit and go to A and B. And if they are vertical polarizations, they reflect and go to A prime and B prime. So one of the things that we recently noticed is that here in front of each collimator, by the way, the collimators are now connected by the fiber cables to our single photon, 4-channel single photon counter, which is also connected to an FPGA, and then give us the result of the single counts and the coincidences using a LabVIEW software. So what we noticed is that we are not getting as much as good data, as much as data that we are expecting. And when I talk to other colleagues who are experts in quantum physics, we noticed that initially I used to have a different type of a filter. And then I thought maybe it's a good idea to get a very small bandwidth filters, which we have here now is 10 nanometer bandwidth filters, to increase the accuracy so we only collect the data that we are looking for the 810 nanometer photon wavelengths that we are receiving from the BBO crystal. But that actually can cause a problem after I talked to the colleagues, because the laser bandwidth, the input of the laser can vary slightly from what we are expecting, which is 405 nanometer, to maybe up to 409 and as low as 402 nanometer bandwidth. And that can cause a problem because that slight variation, then by doubling that, because it's going through the BBO crystal, that bandwidth will, that wavelength will double to 810. That's why we have an 810 nanometer filter. So then 10 meter, like we are allowing only to 815 or maybe 805 only to pass because of the 10 nanometer bandwidth we have here. But that may actually, because of the slight difference in the pump laser, really that can block everything else, which we are expecting to receive. So that is an issue. I already have two of these 30 nanometer bandwidth filter, which I can replace them. That's not a problem, but I still need to get two more, or at least one more, because we are expecting only to have A prime, A and B. We don't need really B prime. That's an extra detector. In our double slit experiment, we only need A prime, A, B, basically three of them. So the fourth one is only for quantum entanglement experiment that we have here, not for the double slit experiment. So therefore, so this is the type of result we are usually getting from our entanglement, quantum entanglement. So for example, we say, this is the number of single photons we get in a half a second. For example, 6,000, 6,000. And the coincidences in half a second is about 5 coincidences. So those numbers are low. And the reason they are low, we realize that that is because we are using 10 nanometer filters. And we have to change that to a 30 nanometer filter. We also have to make sure that we measure the wavelength of our laser to make sure what is exactly it is. So we are going to get a different device also. So basically to make sure that we measure the wavelength of the laser pump. And so actually we know what we are expecting to get. So therefore once we change that, we are expecting to get a much larger number of coincidences and single counts. When we do that, then we are expecting to, when we go back to, I'm sharing now. When we go back to do the double slit experiment, we expect to get a better pattern here. So by the way, each point that we are collecting here, basically what this means is that we are moving one of the detectors, let's say the detectors that I showed you here. So what this data means is that we are moving this detector, one of the detectors, in front of, like in this direction, as I show you by moving my mouse. And then that basically for each position, we are collecting data, how many coincidences between B we get and either A or A prime. And that indicates one of these points. And for each point, we are collecting data, something in the range of maybe 20, 40 seconds for now, but we are going to increase that to a longer time. So to collect longer time data. So once we collect all this data, then we know how many coincidences we get, for example, in 20 seconds or 40 seconds. And then we move that to a next position slightly. Each position is about tenth of a millimeter. So we move it to the next position, collect data, move it to the next position, collect data. And once we move, we move about all the distance or the displacement of about 1 centimeter, maybe 1 centimeter. We collect all this data, and then we are expecting to get that interference pattern that we want. And then the next step would be putting other polarizers in front of the double slit. And of course, then we are expecting to get no interference and all those continuation of the data collection that we are expecting to do and we have to do. Okay, so just a brief update about our work. Thank you.
Okay, well, I'll make a few comments about that to give the listener a little bit of context for that. You saw that line that really didn't look much like an interference pattern. It just looked like noise, basically, with one spike in the middle, which was, it's where we expect the largest peak to be. But as Farbad said, he was taking small amounts of data just basically to see that the system and the experiment was operating properly, and he was getting data, et cetera. When he actually does this experiment, if you notice, there was about 60 points in that little graph that he showed. It's maybe 62 or something, but about 60 points. Each one of those points is taken when Farbad moves that detector 1/10 of 1 millimeter. Okay. Now, when we actually take data in order to get a good diffraction pattern, we're going to have to take that data for about 4 minutes, maybe as much as 5 minutes. So now imagine that you're Farbad and you have this set up and you set it up to your first point, okay, and you now take 5 minutes of data, and then you move the detector 1/10 of 1 millimeter, and then you take 5 minutes of data, and then you move it 1/10 of 1 millimeter and take 5 minutes of data, and you do that for 60 points. So you can see that is basically, you know, the process that he's going to have to go through. Now, he does have the tools such that he can move something 1/10 of 1 millimeter. You couldn't do that with an eyeball. Obviously, you need something that's calibrated that allows you to do that. And hopefully, we don't have it now, but that will be automated with a motor called a step motor, which will actually do that moving. But I don't think we have the step motor in place yet, do we, Farbad?
No, I'll put that once we are more comfortable with our results, our data.
Yeah.
I automate that.
Yes, but for right now, when Farbad does an experiment and makes this data, you have an appreciation that this is going to take him some hours, sitting there without anything changing and anything moving. And then once we see that we're actually getting the kind of data that we're expecting, which we haven't seen yet, then Farbad will automate it, get a step motor, and then he'll be able to set it all up, start it, come back 2 or 3 hours later, and it will be done, and then maybe do another one. But so that's where we are. We're getting close to the point where we're hoping to have good data and we can actually take measurements and do the experiments. So we're getting close, but as yet, we haven't actually seen the data we're looking for. And Farbad happened to discover that one of the problems was a filter we were using, and we may discover other such things as we go. So I don't want to say that, any week now, we'll have it, because we don't know what issues may uncover themselves as we go here. But in any case, I will venture to say we're getting close, ladies and gentlemen. We're getting close, kind of see the light at the end of the tunnel, that we ought to have some good interference data which will enable us to do the experiment not that long from now. How long, I don't know. A week, 2 weeks, a month, 2 months, I don't know. But with a little luck, it won't be as long as 2 months. But it'll take a little luck. We find things as we go. Who knows what else we may have to re-engineer as we go, other than just those filters. But we'll see. So I think that's very encouraging. Thank you, Farbad.
Thank you, Tom, and thank you, Farbad and David, for being here. Thank you for that wonderful, detailed presentation, Farbad, and for all your patient work.
David, did you have anything you wanted to add?
Oh, I think we covered it all. So thank you, guys.
Okay.
Thank
I
you
just
all.
want to add that we don't stop until we get the results. So
Excellent.
it takes.
That's a good thing to add. Yeah, we will just go until we get it right.
Yeah,
however long that takes. So patience, everyone, patience. We're working on it, and we seem to be getting closer. At least we're a lot further along than we were last time we talked to you. So anyway, thank you, Donna, for
Thank
coming
you.
and filming this for us.
Thank you all so much.
Thank you.
Bye-bye.